Okay, welcome to the last day. You made it. You survived. Good job. Okay, so today we're going to talk about some last bits of knowledge that like basically everybody should have. We're talking about so-called complex numbers. Okay. So, how many people have seen complex numbers before? Okay, some of you, not all of you. Okay, so okay, so there's sort of like a problem with the real numbers. And the problem is that you can make equations that don't have any sort of answers. So there are equations with no solutions, right? You can write something like x squared equals -1, right? That's something that has no solutions. Like it's an equation that you can write with the real numbers, but there's no solution in the real numbers, right? So, right, everything up here is a real number. I've got 1 x squared, and I've got a -1 over here, but there's no solution to this. Okay, and so what we do is something. It seems kind of artificial. So seemingly artificially, we just make up a symbol. We create a number. We create something that we're going to call a number, and we denote it by I. Okay, a number I that satisfies x squared equals 1, x squared equals -1. Okay, so we just make up this thing and we say that's going to be our solution. We're going to just create this number I, and we're going to add it into our number system. Okay, and that's going to be a solution to that will be the solution to this equation. Okay. Okay. So then once we throw this number in, then we have these things called these combinations. You can have like things like 1 plus I, right? You can have 1 plus I. You could have like 2 plus I. You could have pi times I. You could have negative I. Whatever. Okay. So basically, you just throw this thing. You throw this thing in and say that this is going to be one of our numbers. From now on, this is going to be one of our numbers, and we're going to treat them like we treat all the other numbers. Okay, it's like a new friend or something like that. Okay, and we require that all the old rules, all the laws, like commutativity, etc. Commutativity, associativity, the distributive property, everything. We require that all those laws still hold. Okay, so if we want to, say add two numbers, like if I say 5 plus I plus 3 minus I, then I can use my laws just as I did before, and I'm gonna I'll have this the 5 plus 3 I can add together, and then the I and the minus I add together, and I get 0, right? So I minus I, these guys cancel each other off, right? You just get 8, right? So just like you basically have these sort of pairs of sort of complex numbers is what we call them. Complex numbers where it has this real part and it has this imaginary part, but you just treat them as if they were numbers. Okay, so for example, right, like if I have say 5 plus I times 3 minus I, well, you're just going to use the distributive property, like you did with normal numbers, right? And so you say, okay, this is going to be 15 plus plus 3i, right, 15 plus 3i, and then we've got negative 5i, and we've got negative I times I plus negative I squared. Right? Does that make sense? Right, so we're just using the distributive property like we do with with any old numbers, or just like we're doing things with x, right? If we have 5 plus x, 3 minus x, right? That's going to be 15 plus 3x minus 5x minus x squared, right? So you just think of that's maybe the way you want to think about this, right? That this is some sort of just some symbol that you're going to throw into the numbers, throw into our old numbers. Okay, so so let me put up the definition here. A complex number is an expression of the form a plus bi, where a and b are real numbers, and I is this thing that solves I squared equals -1. Okay, so right, like this is a 5 plus I over here. This is a complex number, right? And we call A is called the real part of the number, and B is called the imaginary part. Okay, so often one denotes the complex number by, how in the real numbers we use the variables x and y. In complex numbers, people tend to use w and z. Okay, for the complex numbers, or Greek letter zeta. So people will just use z for now. So z, you have some complex number, and you call it z. Z is this complex number. And the notation for these things over here, for the real part, one uses this kind of fancy-looking, RE, and then some sort of fancy-looking IM for these notations. This is how one writes the real part and then the imaginary part. You can just write RE and IM. You don't have to write it in fancy cursive. Okay, so this seems like kind of a weird thing to do, right? We just adjoin this symbol to our old number system, and then we create this new number system. Okay, we create this new number system which satisfies all the same rules as the old number system. Okay, and you just work with it as you might as you would normally. Is a graphical representation of this. Of the complex numbers. We represent them on the plane. So we call this thing the imaginary axis, and then this thing the real axis. The imaginary axis and the real axis. And then you just say, like, if I want 1, so 1 is here, this is 1, and then this is I, right? And so 1 plus I is this guy here. Okay, 1 plus I. If I wanted 5 plus I, that would be over here. 5 plus I, cetera, et cetera. So it's just like, if you, 1 plus I corresponds to 1 comma 1, right? 1 plus I corresponds to 1 comma 1, 5 plus I corresponds to 5 comma 1, and so on and so forth. So you take your complex numbers, a plus bi, and then you switch them over to a comma b, and then represent them on the plane here. Is that making sense? Right? So like, where would negative I be? Where would negative I be on this picture? Its real part is 0, right? And its imaginary part is -1, right? So it's going to be at 0, comma -1, right? So negative I is here, right? This is going to be 0, comma -1. Okay. Okay. And you don't really have to know this, but let me just throw out some words that are often associated. If I have a complex number z, then this length here is called the modulus. Modulus of z. Okay, and it's denoted. So let me erase this. Things are getting too cluttered. Okay, if I have a complex number z here, a plus bi, say. So this is a, and this is b, right? Then this length here, is denoted with the absolute value sign, just like you might expect, right? It's the length of this, the distance from the origin of this guy, right? And it's called the modulus of z. And then this angle here. This angle here is called the argument of z. Okay. So modulus and argument. Modulus and argument. Those should look kind of familiar. Remember what we did last time with polar coordinates, right? This modulus is basically your r. This modulus is your r, and the argument is your theta, right? So it's the same. It's just different words. Okay, we're in the complex world that r is called modulus and theta is called the argument. Okay, so nothing fancy. Okay, so let me just put up basic algebra, which is kind of as you would expect. If I have a number a plus bi, and I have another number c plus di, then what do I mean by z plus w? Turn to a neighbor and say, he just means this. Okay, yes. Now people are smiling, which is good. You all look kind of nervous, but now you're smiling. Good. What do I mean by this? Anybody? Now you're looking nervous again. Stella.
You just add all the terms to like a plus b plus c plus d.
Yeah, so it's going to be a plus bi plus c plus di. And if I regroup things, I'm going to regroup the real parts. This is going to be a plus c plus b plus d. Right. Don't. This is something very simple, right? If I have 5 plus I and 3 plus I, and I add them together, I'm going to have 8 plus 2i, right? That's all I'm saying here. Okay, nothing fancy. Z times w is a little bit trickier, but it's a little bit trickier to write down, but easy to work out. So when I say z times w, what do I mean by that? That's going to be, of course, a plus bi times c plus di. Right? So can anybody read off what that's going to be? This is actually a little tiny bit tricky. What's going to be the real part? The real part, and then I'll have the imaginary part. Can anybody tell me what the real part's going to be? Just by looking at it, working it out in your head, maybe. Take 20 seconds and see if you can just multiply this out and then tell me what the real part and imaginary part are. Okay, turn to a neighbor and say, turns out to be this. Okay, somebody tell me what I should do when I'm multiplying these out. What am I going to get here? This thing times that thing, what am I going to get? Anybody? Stella, go ahead.
So we're saying AC plus CBI plus ADI plus EDI squared, but the I squared will just be 1, so negative BD.
Yes. So this thing turns into negative BD. Exactly. Right? So you use the distributive property, just like this were, this just as if these were real numbers, and you multiply it out, and you see that the real part is going to be AC minus BD, and then the imaginary part is going to be AD plus BC. So this thing turns into negative BD. Right? So, yeah. So that's how multiplication works out. Don't try to remember this. It's not really worth remembering this. When you have two complex numbers and you want to multiply them, just multiply them, and then you'll just use the distributive property on it. And remember that I squared is negative 1. Okay. Let me introduce, so there's kind of we use this thing to denote the reflection of of Z. So if this is Z, then we reflect it across the real axis, and we get this guy here, Z. So this is A minus BI. Okay. And it has a name, it's called the complex conjugate. Okay, so this is the reflection of that. What happens if we take Z and multiply it by its complex conjugate? We have A plus BI times A minus BI. Does anybody want to read it off, what you get here? Just using the distributive property. We get A times A, right? So I put this A squared. And then we would get ABI, we'd also get a minus bi, right? So we get abi and negative abi, so those guys kill each other off, right? And then we get bi times negative bi. What's that? Bi times negative bi. Well, we get b squared I squared, right? So we get, I'm sorry, negative b squared I squared, right? But I squared is negative 1, so we're going to get just b squared, right? We would get bi times negative bi, right? So that's negative b squared I squared, but the I squared is negative 1 again, so we're just going to get a b squared. So we get a squared plus b squared. Okay. A squared plus b squared, which actually is geometrically, that's the square of the modulus, right? The modulus, remember what the modulus is, it's the distance from the origin. But the distance from the origin of this point AB is the square root of a squared plus b squared, right? So you notice that this thing is actually the square of the modulus. Okay. Are people getting this, or people okay? Everybody all right? Okay. So all we said is that we create this new number system we create these new numbers by throwing in the square root of negative 1, right? And then we say that when we add, we're going to use our basic laws. When we multiply, we're going to use our basic laws. Okay. So it's just it's just like what you would expect. The dividing is a little bit tricky. So the definition of division is a little bit funny. So what happens is, here's how we define division. If you're dividing a complex number by another complex number, you define that as z times the conjugate of this guy, z times the conjugate over the bottom guy. Okay, and then divide that by w times its conjugate. Okay. Let me do some examples, and everything will become clear, I hope. So let's just do some examples of working with complex numbers. Okay, so I think this is something that really everybody should be able to do, just like a basic skill that you have if you want to go into higher, if you want to keep on going in your math. Okay, so let's do some examples. Okay, so here's the first one. 2 plus 7i times 2 minus 7i. So what's going to happen here? Take 15 seconds and see if you can work it out. You could use the formula over there, or you just work it out directly. I think it's probably better practice just to work it out directly. Okay, so just in the interest of time, let me do it. So, just as usual, we're going to get the 2 times the 2, right? So that gives us 4. We're going to have 2 times negative 7i, that's negative 14i, but we also have this one, which gives us 14i, right? So we've got negative 14i, we've also got plus 14i, and then we've got 7 times, negative 7 times 7i squared, right? So that gives us negative 7 times 7, I squared, makes it positive, and so we get this, right? These guys cancel off, and we get 53. Everybody get that? Okay, great. Right, and right, and recall that that's actually the modulus squared. So this tells us that the modulus of this is the square root of 53. Right, the modulus of 2 plus 7i, right? 2 plus 7i is 53, which you know already because this is just the point 2 comma 7, right? And so its modulus is the square root of 53. By the Pythagorean theorem. This is 2, this is 7, and so this is the square root of 53. Okay, so here's now let me give you an example of division. Negative 1 plus 3i over 2 plus 7i. Okay. And so the rule is just multiply that guy by the conjugate of the denominator over the conjugate of the denominator. Okay. So you get 2 minus 7i over 2 minus 7i. Right? We know what we're going to get on the bottom. We just work that out, right? We just work that out. That's 53 on the bottom. And then on the top, we've got negative 1 plus 3i times 2 minus 7i. Right? And then you just work out the top, as we just did, just over here, right? So we get, should I let you do it? Just for practice, take 10 seconds and work out the top. Negative 1 plus 3i times 2 minus 7i. Okay, so negative 1 plus 3i times 2 minus 7i over 53, right? So what do we get on the top? We get this negative 2, we get 6i, we get positive 7i, and we get negative 21 I squared. And so we get 19 plus 13i over 53, right? So 19 over 53 plus 13 over 53i. Okay, is that all right? Everybody, did anybody not get that? Anybody not get that? Okay, so you see how to divide, right? You see how to divide, right? You multiply by 1. You multiply this by this 1 so that you get a real number on the bottom, and then you can just divide. And then you know how to divide by real numbers. That's basically what this trick does. It changes the bottom into a real number, right? The bottom turns into this real number, and then you already know how to divide by real numbers, right? So you've got this complex number divided by a real number, but that's easy. Okay. So. Okay, last example. 1 over 2 plus 7i. What's that? I'll let you figure that out without any hints. Turn to a partner. Can you say something? Okay, somebody tell me what I need to do. I've got a complex number over a complex number. I'm dividing something by a complex number. So what do I do? Right, multiply by the conjugate, right? Multiply by this funny looking one. Okay, and so what happens, right? I'm going to get 2 minus 7i on the top, and I get the 53 that we had before on the bottom. And so this ends up to be 2 over 53 minus 7 over 53i. Okay. So that's anyway. So this was just to tell you about complex numbers and give you at least the basics of how to do arithmetic with them. Okay. Complex numbers turn out to be this kind of really amazing extension of the numbers that, for example, it turns out that not only does this equation have a solution, but in fact, any equation that you make up will now have solutions. Okay, it's not just this equation has a solution, right? If I make up, some great wacky, whatever equation you make up, it will now have solutions because we've somehow expanded our numbers big enough so that all of these things will have solutions. Okay, so that's kind of a miracle that occurs. There in the real world, there are some people who say that actually time should be considered as a complex number. That in physics, that if you make time a complex number, then that solves. I've forgotten what it is. It solves. It makes some sort of problem. I should. I'm sorry. I'll find out what kind of incredible thing this is and then tell you what it is. But I've forgotten it. Darn it. I wanted to mention earlier, does anybody know the author Haruki Murakami? Yeah? In one of his books, he talks about his character and he says, caught in the crosshairs of the real and the imaginary. So his character's going along and something really strange happens. And he's like, caught in the crosshairs of the real and imaginary. He's talking about the complex plane here, right? He's here, caught in the crosshairs of the real line and the imaginary line. And that's a lot of how Haruki Murakami's books start off. He starts off here and then he starts slipping into the sort of combination of the imaginary and the real. But that's not math, that's just something, that's just a metaphor. Okay. Darn, there's one more thing I'd really like to show you. I don't know if I have time for it. I hope I don't have time for it. Yeah, I don't have time for it. Sorry. Maybe I'll make a recording of it and I'll send it to you guys later. But yeah, there's actually this connection between the complex numbers and trigonometry, so that all those formulas that you had to learn and remember become completely trivial. you can just calculate them using the complex numbers, using complex numbers. Sorry, I have to say, I have to tell you. Okay, so there's this thing called, this, don't worry about this, this is not in your exam, right? Okay, this is just something that you should see. There's something called the Moivre's formula, or also called Euler's formula. I'm not sure who deserves the credit. And it's the following. It says that if you take e and raise it to a complex power, then actually the number that you get is cosine theta plus I sine theta. Okay. So there's this relation between e and the trigonometric functions. Okay. Right. That e to the I theta actually turns out on the complex plane to be cosine theta plus sine theta, right? Which is just this point of angle theta, this point of angle theta. And this e to the I theta satisfies, you know, the rules of exponents that you would expect. Yeah, I don't really have time to do this. Sorry. I'll make a video and then I'll send it out. But yeah, what you'll see is that it's actually really easy to get the cosine, so if I look at e of theta 1 plus theta 2, that's going to be cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. Right? So just plugging in a sum here, I get this formula. Right? But remember, this thing is ei theta 1 times ei theta 2. Right? Because this thing is an exponent, right? It's e to the something. You've got this sum, you know, you can use the rules of exponents on it. Right? And so what do you get there? That's going to be cosine of theta 1 plus I sine theta 2 times cosine of theta 2 plus I sine theta 1, I sine theta 2. Right? Right? I'm just using de Moivre's formula. Right? This is this, and this is that. Right? And then you do complex multiplication. You get cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2, sine theta 1, sine theta 2, and then you get the imaginary parts. You get plus cosine theta 1, so you get I times cosine theta 1, sine theta 2, plus cosine theta 2, sine theta 1. Right? But look, the real part over here must equal the real part over here. And that's your addition formula. That's the addition formula for the cosine. Remember that? You've seen this, right? Cosine of theta 1 plus theta 2 equals cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2, right? And the addition formula for the sines also pops up in here. Okay, so you actually can get it out of there. Okay, now I've really used up too much time. Sorry. Okay, well that's the end. That's the end of the course. That last part, don't worry about it. It's just to show you that things are cool, right? That things in mathematics actually are really, really amazing. And if you go on, you'll see more and more cool things. So I hope you do.